Welcome to Chemistry with Science Mom and Math Dad. We're super excited to have you here. And I want to show you a quick outline of how our course is going to be run. And then we'll give some shout outs to those who are watching live and a special welcome to you if you're watching the replay. So every lecture or lesson, we are going to have a little welcome. And then we have a question of the day, a story, a Chem-Mystery. Get it? Chemistry, Chem-Mystery.
I see what you did there.
Polls and a science demonstration followed by questions and answers. So if you have good questions, put them in the chat. Our moderators will be gathering them. Special thank you to Science Mom Amber and Science Mom Jamie, Science Mom Krista, who are moderating for us in the chat. And a shout out to Noah and Hadi from Ottawa, Aiden and Audrey watching from Massachusetts, Leia, Maya, Annie, and Yubi watching from Oregon, Torrance family in Puerto Rico, Marine Man watching from Texas, Ruthann Joshua from Missouri, Zara and Azu from Ottawa, Sydney and Seven watching from Florida. Do you want to grab a couple more, Math Dad?
We got Katie, we got Pickle Obsessed from Minnesota, Minor Master, Vivian Awards, Sagar, Kat Brian
Garcia.
Goldberg, Wayfaring Kids, Vivian Allward. We've got a great crew here today. You guys were in the chat early saying hi and answering questions. We are super excited for what we have to share today. I want to draw your attention down to the link in the description. If you want to, you can download the
notes. We have chemistry doodle notes, and you can draw along with us as we go through this lesson.
That's right. So I wanted to give you the heads up on that. But yeah, thank you for joining us. This is going to be a lot of fun.
And a quick note about our chat rules. Make sure that you are respectful, stay on topic, and no spamming that's like long drawn out words or repeated words because it makes the chat difficult to read, and no sharing personal information like your email address or where you live, like your street address. So those are our rules for the chat.
Follow the golden rule. Make sure that you're treating others the way that you would like to be treated, and we'll all be better off for it.
So Math Dad, are you ready for our big question of the day today?
I'm very curious. What is our question of the day?
Today's question is, why can you light some things on fire and not other things?
Why can you light some things on fire and not other things?
And this question is even better if we kind of act it out. So quick little demonstration here for our science question of the day. This is something you should not try at home unless you have adult permission and adult supervision, because we're going to be using fire. So Math Dad, safety first. Here are some gloves.
Uh-oh.
He's getting nervous, you guys.
Anytime she breaks out the big gloves, I wonder if we should be doing this indoors.
And safety glasses, because you only have two eyes. You want to protect them both.
Yes, I do.
And now here is the first object that we're going to try lighting.
These goggles don't.
Oh, they don't fit over your...
Nope. Okay, we're good. I can't see, but I'm wearing... My eyes are safe.
Here's a spoon. A metal spoon made out of steel.
And I have to bend it?
Nope. Just hold it there. And I'm going to try and light it on fire. Do you feel nervous? What's your prediction? What do you think is going to happen?
It's not going to go on fire?
And you're correct. We can heat it up and it's going to get hot. But this is not flammable. This spoon is not going to be something that we can light on fire.
It looks a little scorched.
It did get a little bit brown there.
It's kind of smells bad.
Mostly particles from the propane that was burning that got on here. Now next, I'm going to give you a paper towel to hold.
Okay, and what are we going to do with
this? I will point out to everyone who is watching, we have a big bucket of water right here, because anytime you're doing something with fire, you should have material on hand to put out the fire. And Math Dad does have heat-proof gloves.
You're not going to light this on fire, though, right?
Oh.
You are. She is, guys. And now what?
And now it's burning. This is flammable. You're supposed to put it in the water. There we go. The paper towel is flammable, but the metal spoon is not. And the question is why? This is a question that people have been asking themselves since antiquity. Why can you use sticks to light a fire and grass to light a fire, but the rocks don't light on fire? What are things really made of? This is the central question of chemistry, and this is what we're going to dive into when we talk about the story of the atom.
Is it just things that have air in them? They burn?
No.
Oh, okay.
We'll
I was going to try to spoil it for you, but no.
We'll be getting right into it. So obviously, these are two very different materials. One of them is hard, and you can eat cereal with it. The other one, if you tried to eat cereal with it that was in milk, it would just dissolve and turn into a big mess. And to understand what things are made of, we need to go back in time and talk about how this question has been answered at different points in history. Because depending on where in history you were, the answers to this question would be very different. Let's start by going to ancient Greece. And if you have the notes, you can color along with me as we travel back in time to Greece. So I'm going to switch our screen right here, Math Dad, if you'll bring us on down. I have an iPad here with the notes on it. Hopefully you can see it there. And if you have the notes printed out on page 1, you can color along with me. So to understand,
page 1 is actually the 6th page of the document, or
yes,
something like that.
We have a table of contents and supply list first. So what are things really made of? Well, in ancient Greece, you had certain philosophers who had a debate about this. Some of them said, oh, and Math Dad's signaling me, he's like, zoom in, make it bigger. So some of them said that you could just divide things in half and keep dividing and dividing, but eventually you would get down small enough and you would reach something that was uncuttable. And they called this atomos. So these small little particles that made up everything were called atomos, that's where we get the word atoms from.
So like a piece of cheese.
Cut it in half, you have 2 pieces of cheese. Cut those in half, you have 4 pieces of cheese. And if you keep going, eventually you would get to a piece that was so small, it couldn't be cut in half anymore, but it was still cheese. That is what the ancient Greek philosophers thought. And some of them, there was a bit of a debate because some of them thought that there were infinitely many types of these atoms. And others said, no, that doesn't really make sense, because if a cheese is made out of a cheese atom, then does it just spontaneously appear from milk because you use milk to make cheese? And there was some debate about this, and they didn't really understand it, but that was their basic idea, that you have these little tiny particles that make up everything around us. Then we kind of went backwards. If we go forward in time to Western medieval Europe, we have the idea that everything is made of 4 elements. You have water, you have earth, you have air, and you have fire. And the different amounts of these that you put together give you different things. So if you went into the Middle Ages and asked someone, why can I light this paper or grass on fire, but I cannot light this spoon on fire? They would say, well, the spoon has more water and earth in it, obviously, and the paper has more fire and air in it. And that's why when you give it a little heat, it turns back into fire and air, because that's what it's made out of.
So that seems more simplistic than what the ancient Greeks had.
Yes, but it also has some big problems because it doesn't really explain what we observe and how you can get multiple things reacting together and why you can have reactions that are reversible. So there are a lot of things that this did not explain. And then we have the discovery of, or the kind of the creation of alchemy, the alchemists. And there's a fantastic painting, Math Dad, if you'll throw that up really quickly. This was a painting, it's a common domain image. It was made in the 1600s, called Explosion in an Alchemist's Lair. So alchemists had several goals. These were sort of like the early chemists. They were trying to change one element into another. That was one of their big goals. Like, can you take lead and can you turn it into gold? And they also were looking for the font of immortality, and they thought that there was a philosopher's stone and that you could find a panacea that would cure any disease. And they had a really hard time reaching these goals because they're impossible. Isaac Newton was really laid the foundation of modern physics, and his ideas and his formulas that he created, we still use today. But he was completely stumped when it came to chemistry because it turns out you cannot turn lead into gold. It doesn't work. So alchemy had some big problems with it. But one thing that it got right is there are more than 4 elements. We don't have things being made up of earth, air, water, fire. You have elements like gold and silver and mercury and other metals that they've discovered were pure. And the elements that were pure, like gold and silver especially, they valued those, and they were like, oh, maybe we can make these. And they did make fool's gold. If you take iron and mix it with sulfur and you get iron sulfide, that's pyrite. And it looks kind of like gold. It's shiny like gold, but it doesn't have the same properties of gold and that's why we call it fool's gold. It doesn't quite work.
Are you supposed to be coloring this as you go? Or?
Oh, you definitely can color. And you don't have to go as fast as I go through this. You can color it on your own, but it's just and you can write other things on it too as you want. So then that brought us to the early 1800s, and a scientist named Dalton discovered that, you know what? When you are reacting one thing with another thing, you're getting ratios. Like if you burn this thing, it always comes out in a 1:2 ratio or a 1:1 ratio. And so he said, this proves that there are particles, that the stuff around us is made out of particles. The Greeks were right, and the alchemists were right too, and these particles have different sizes, and they react differently, and when you combine them together, you can get new compounds. And he called them atoms again, and said that, you know, it's the smallest thing that you have, and you can't cut it in half, and that's all we have. And that model was around for quite a while until we discovered electricity, and people got really excited about this contraption here called a cathode ray. I'm going to ask Math Dad to throw up a picture. So this is what a cathode ray looks like before you turn it on. It's just a glass tube, and we're going to take out the air. Most of the air is taken out, so it's almost a vacuum of empty space inside. Almost a vacuum, not quite. There's just a tiny bit of air in there. And watch what happens when we turn on a current. Ooh.
Pretty lights.
Yes, this fueled like 40 years of research, because the person who invented this, everyone else was like, oh la la, what is going on? We must find out. And for 40 years, scientists were researching and trying to figure out exactly what was going on in these cathode rays and why did you get those amazing colors of light. And J.J. Thomson figured out that, in fact, yeah, you can go ahead and remove that. In fact, what was happening was that you had this path of electricity going through, and these negative particles were then getting excited, and that's what people were seeing. So he discovered the electron, these negative particles that were so small, they were 1,000 times smaller than a hydrogen atom. So hydrogen had been discovered at this point, and hydrogen is a pretty small atom. Let's say hydrogen is that big. Well, these little particles, and my pen wouldn't draw the dot small enough, but 1,000 times smaller, 1,000 times smaller than hydrogen. That was amazing. But the other amazing thing—
So smaller than an atom.
Smaller than a hydrogen atom, which is the smallest atom. Because at this point in time, people knew that there were different elements. They knew that hydrogen was different than gold, and a hydrogen atom was way smaller than a gold atom. But they didn't really understand what atoms were made of. And this was the discovery of the electron. So these particles, they were 1,000 times smaller than a hydrogen atom, but they were charged. They had a negative charge. And this little bit here about them having a negative charge, that's super important. And that was super surprising, because are atoms charged? Most of them, no. A hydrogen atom does not have a charge. So how could it have a negative charge? Well, let's travel over here.
So I've got a question for you here. So first of all, before we advance here, Chloe wants to know, are we in space?
Are we in space? That would be awesome if we were. If we were in space, you guys, I would not be teaching like this. I would be like upside down with my hair flowing out, and I would be flying all around the room, because experiencing 0 G's, zero gravity would be awesome. We are not in space, unfortunately. This is a backdrop. You can see if I push on it, but it looks really cool.
Oh, I was going to tell them that we were in low Earth orbit and we'd be back one of these days, but no.
Oh, that's where we're at. So back to the electron. Electrons are negatively charged. So the only way to explain how atoms could be neutral is if atoms were made of sort of, whoops, and I didn't realize I still had my highlighter on. I'm going to go back to the pen. So here's an atom. It is a sea of positivity. All this blue represents positiveness, and then you have these little negative particles in there. So they said, okay, that's what atoms are. But then a little bit later, there was an experiment done where they took these sheets of gold foil and they were shooting particles at them. And if this is what atoms looked like, this, you know, sort of, it almost looks like a chocolate chip cookie, then all of the particles should just go straight through. But some of the particles bounced back. And that told everyone that there was this thing called the nucleus. Oh, and I thought I was going to be coloring in, but instead I'm coloring over. I'm sorry, little nucleus guy, you just got swamped. There was a nucleus, and the nucleus is made of neutrons and protons. And it does have a positive charge. And then the electrons, they're going around the nucleus. So the discovery of the nucleus was super exciting, but then it gets even more bizarre as we learn more about what makes up atoms.
Okay, so just a sec. So they shot particle or electrons through this, or what was passing through it?
Let me go back real fast. So they had alpha particles that they were passing through this. Whoops. They were passing through, and some of them went through, but some of them would bounce back. And the only way they could bounce back is if they were hitting something that was really dense and solid. And they realized that all of the mass, instead of thinking about an atom as like a really big beach ball, they realized, holy cow, it's more like there's a beach ball size space it's occupying, but there's really just a marble in the center, and that hard marble, some of these particles would hit it and bounce back. So that was the discovery of the nucleus.
Okay, and wow, that's pretty crazy.
Yeah.
Because these are particles that are so tiny, we can't actually see them, right?
Yeah, super tiny. So I mean, they were detecting the particles with different sheets of metal and things like that. But it was a really surprising discovery. In fact, Rutherford, the scientist who discovered this, he has this great quote where he says, "It was the most surprising moment of my life. I wouldn't have been more shocked," or he says, "It was just like if someone had held up a piece of tissue paper and then shot a gun at it, and then the bullet bounced back off of a piece of tissue paper." That's how unexpected it was for these particles to bounce back. They were really surprised. Now I want to talk just a little bit more about electrons, and we will be getting more into electrons in a future lesson. But electrons are crazy, you guys. These particles are small, and we can't know where they are and how fast they're moving at the same time, which is really kind of weird. There's some strange things about electrons, but they do like to be in pairs. These little arrows here indicate that there's a pair of electrons. They really like to be paired up, and they exist in orbitals, which we'll be talking about more on Friday. And then I already mentioned that the nucleus has neutrons and protons. So the discovery of the neutron came later, after people had discovered the electron and the proton. But when they discovered the neutron, that explained why some elements are heavier than others. Because it turns out that if you have hydrogen, the lightest element, it's actually just one proton, and then we have one baby little electron circling around it. And I'm going to make my proton a little bit bigger. But if you add a neutron, and how do I get a different color, Math Dad? There we go. If we add a neutron to this proton, then we have deuterium. So this is deuterium, and this is hydrogen.
So deuterium is not hydrogen.
It's a different form of hydrogen. And because hydrogen is such a common element, and because scientists were so impressed and amazed by this, we gave it its own name. Usually with isotopes, and again, we'll be talking about this more in a different lesson. Usually with isotopes, we don't give them their own name like this. We just say, oh, it's carbon-12 or it's carbon-14. But with this one, deuterium, they gave it its own name because it was like, whoa, this weighs twice as much as the other hydrogen and it acts really differently. So there are two types of hydrogen, and that's all due to neutrons.
So it has one proton, one neutron, and those are both making up the nucleus.
In the nucleus. Yep.
Okay. And the electron always goes around the outside.
Correct. Okay. Correct. Math Dad, check on the chat real quick as I go to page 2, see if we have any questions we want to answer real fast. And then I am going to scroll down to page 2. You can join me.
There are some compliments on your drawing.
Oh, thank you. Thank you very much. We are going to now draw in these models of the atom and how our idea of the atom changed over time. So if you have the notes, you can turn to page 2 and you can color along with me. We're going to fill this in. So we started out in 1803 with John Dalton saying, it's official, guys. There are atoms. We know several of them. They all have different sizes and weights. But if you have an atom, it cannot be cut up. So we're just going to draw a solid sphere here. It is a solid lump of stuff that cannot be cut up. And my lump is not super round, and that is okay. It has character. Yeah,
there we go. I got to say, at first glance, that looks entirely plausible.
Yeah, not a bad theory.
Yeah, what's wrong with it?
The wrong thing is that the atoms are not the smallest particle. There are smaller particles. And so when we discovered electrons that are negative, that was very exciting. And now we had to come up with a different model, a different way to explain what atoms were. And so we call this the plum pudding model because it was discovered by an English scientist, and English scientists apparently are big fans of plum pudding. But I would like to just say that this should be called the chocolate chip model. Chocolate chip. Because that looks a lot more like a chocolate chip cookie than a plum pudding to me, don't you think?
Yeah.
So the idea here was that this area is all positively charged. And each of the little chocolate chips, or plums, if you are into plum pudding, is negative, and that they're all mixed together, but you can separate them. You can separate the plums or the chocolate chips. You can take those out, because that's what happened in cathode rays. The electrons came out. And this one worked pretty well, except the problem was there was no nucleus in this model, And we did discover with that cool experiment, we discovered that atoms, in fact, do have a nucleus. And now, does this look more familiar to you guys? That's kind of what we think of when we think of an atom, right? It's a really common icon that you'll see all over the place. This is the planetary model, and the planetary model works pretty well because you do have electrons orbiting a nucleus, and the nucleus is positive. But this one didn't quite predict how electrons behave, because if they were just going around in circles like this, all at the same distance, they actually should eventually collapse in and run into the nucleus, and that doesn't happen. And there was a scientist named with the last name of Bohr, Niels Bohr, who came up with a different model where you have orbitals. Well, this is a little ahead of orbitals, but different levels, that's what I wanted to say. You have different levels in your atom. And in the first level, does anyone remember how electrons want to be? They always want to be in...
I know.
You know?
It was pairs, right?
Pairs. They always want to be together. So we have two little electrons here, and now it kind of looks like a face. I'm going to undraw that smiley face. Two electrons in pairs in our first orbital, and that's that first level of where the electrons can be. And then in the second level, guess how many we can put in there, Math Dad? How many electrons?
4, 8?
8.
There we go.
8 electrons in our next level. And then you can keep going up and up and up. And we still use this type of drawing to talk about atoms today because it makes it really easy to see what the electrons are doing and which ones are paired and which ones are not paired. But the problem with this model is that it doesn't really explain what happens when you get to larger atoms. And so the model that we use now is talking about electrons in orbitals. And we're going to get into more of that on Friday.
So do these electrons, so they're on the outside, are they traveling around?
They have an area.
Put?
They're moving. They're moving all the time. They have an area of space that they occupy that's called an orbital. And you can know with a high degree of certainty that the electron is in there somewhere, but you can't know exactly where it is unless you, electrons are weird, you guys. They're crazy and weird and exciting.
Probability cloud, is that what it is?
Yes, a probability cloud, that's what it is. Let's come back to this other view real quick.
All right.
So that concludes our science story. And do you remember what comes after the science story, Math Dad?
Some befuddlement that I can't believe we're able to answer the questions that were posed there, because when you think about things that are so small that we can't see them, how could we possibly study them? So I'm just really impressed. The scientists were able to come up with some tests that could answer some of these questions.
It's pretty amazing.
Because it just sounds like, we'll never know. I'll move on.
To just illustrate how small atoms are, an atom is so small, it has no color because it's smaller than a wavelength of light. So if you were able somehow to shrink yourself down so that you were as small enough to see atoms, you wouldn't be able to see any color because they're so small. They're smaller than a wavelength of light. And that's how we see, is by wavelengths of light coming in and reaching our eyes. Isn't that crazy to think about? And electrons are even smaller, 1,000 times smaller than an atom.
Okay, you're breaking my brain here.
It is time for our chemistry now. And I did see a couple texts from our excellent moderators in the chat, Science Mom Jamie and Amber. So if you have questions, put them there, and we will do some Q&A in a minute.
Okay.
But first, we're going to have our Chem-Mystery.
Okay.
So here, Math Dad, you scoot to your side, I'll scoot to my side.
All right, it says, known since antiquity, a metal quite liquidy, used in barometers, sometimes thermometers, handled with care, of poison beware.
Does anyone know what the answer is to this chemistry? What element are we talking about? If you know, put it in the chat.
Okay, I think I know the answer. So
I'm going to read it one more time.
I'm going to hold off. Go ahead.
Known since antiquity, a metal quite liquidy, used in barometers, sometimes thermometers, handled with care, of poison beware. And shout out to Ibrahim, who said mercury. That is 100% correct. The answer to this is mercury. And mercury is an element that we've known about for a long time, because as people would mine, this was an element that doesn't bond very well with other elements. And if you get into an area with a lot of mercury, sometimes it would just ooze out of the side of the rock.
Oh, wouldn't that be weird? Like metal is oozing out of rock?
Metal. At room temperature, mercury is liquid, which is kind of crazy. Now, it's toxic, but it all depends on what type of mercury you have. So my dad, actually, when he was a boy, he had a little chemistry kit, and the chemistry kit came with a little vial of mercury, and he used to play with it, pouring it on one hand and then to the other hand. There are certain types of mercury that you can handle on your bare skin and you're not going to get sick or poisoned. But there are other types that are very poisonous, where just one drop on your skin could actually kill you. And
wait, do they still sell these kits?
No, it's a bad idea.
Okay.
Bad idea to handle mercury with your hands. So you don't find kits like that anymore, because we know a bit more about radiation poisoning, and also we're more careful now about a lot of things. But radiation poisoning and toxicity of metals like mercury and lead, we're definitely more careful about now than we were 40 years ago. And so you can't find kits like that nowadays.
Man,
thank goodness.
So in the chat, AM says, did you know Abraham Lincoln used mercury?
You know, it used to be used as a medicine, which an emperor in China took enough mercury as a medicine that he actually died from mercury poisoning. And as he was getting sicker and sicker, I think the thought was he just needed to drink more mercury to get better, because it was a medicine, but it turned out like it's not a good medicine. Not a good medicine.
Yeah, got to make sure we test those things. I'm really glad that we have a better understanding of toxicity today. And
Anna has a good question. Why are some kinds of mercury more poisonous than others? It depends on what the mercury is bound with. So there's a form called diethylmercury that is incredibly poisonous, where just, a drop could be enough to actually kill a person. But pure mercury that's not bound with anything else, its toxicity is fairly low if it's on your skin. But if you breathe it in, inhale it, because it's a liquid at room temperature, it actually can turn into a gas as well. And if you inhale it, that's when it becomes really dangerous, if you breathe in mercury vapor. But that's a little bit of a tangent.
Okay, so what happened to your dad? Ruth Anna wants to know.
Oh, good question from Ruth Anna. My dad is still alive. He's 77 years old, and he went to medical school, became a doctor, and worked in an ER for more than 40 years before he retired. And he's very healthy. So he's just fine, because the type of mercury that he handled when he was a kid was pure mercury that was not extremely toxic. But still, if he had breathed in a lot of that, if he'd breathed it in, he would have gotten really sick.
There was a request to just take another look at your model here.
Yeah.
And so this is mostly a way of keeping track of the behavior.
Keeping track of the electrons. And if I were to do this sort of color-coded, let's go back here to my pen. Here's the electrons in this model, and here are the electrons in this model. So if we were to, color code the electrons, that's kind of what it would look like.
Gotcha. So, and we're going to go into more depth on that in days to come?
We will. So if it seemed like we went through that really fast, no worries, because we are going to go in a lot more detail about electrons and different types of elements in future lessons.
All right, so this is just the introduction. Okay, good.
Just an introduction. And the things that I really hope you got are just that there are particles that are smaller than an atom. And we actually have a couple polls just to sort of see, did you guys catch that? Did you catch which particles are smaller than an atom, and which one has a positive charge, which one has a negative charge? So we have a quick little quiz all about protons, neutrons, and electrons. And if you received our email, then you got a link to item poll. That's how we're doing these little polls. And Math Dad's going to grab it and put it in the chat.
Itempool.com/live. I will paste that into the chat right now. And maybe.
Yep.
Okay.
There we go. So you can open this up in a new tab. And if you would like to vote, then as soon as we open up the question, you can vote. Is that first question unlocked?
Nope, I'm ready to go live.
All
so
right.
If you've gone to that site, I'm going to begin accepting questions. And our first question is, which subatomic particles are positively charged?
Is it protons, neutrons, or electrons? Which ones have the positive charge?
Is it one of them? All three of them? Just two of them?
Oh, you made it so they can click more than one.
Yeah. So who knows? So it's an interesting question, and once again, it's really cool that we can even ask that question, because we know so much just considering the size of these things.
Yeah.
It just breaks my brain to think of things that tiny, and that makes it super impressive that there are some answers. So if you look on the screen, you should see some answers coming in there.
And we're going to use this same poll. And if you're watching the replay, you should still be able to get to vote. We'll use this same poll each time. And so when we put up the chemistry, that's sort of like a signal to get your item pool /sciencemom/live link ready. And then you'll be all ready for the questions for for us to vote.
So I see a leading contender here.
There is a leading contender.
76 votes. The second place is around 30-ish. Oh, okay, those votes are coming in. This is fun. I'm glad we're getting this figured out. And
we just passed 100 votes for our top one.
So there's no reward for getting it right other than the satisfaction of knowing that you got it. And there's no penalty for getting it wrong. We're just trying our best here. And yeah, we're learning as we go. But yeah, I like this poll because you don't see which one's getting the most votes.
I sure hope it's the one I think it is. We'll find out in a minute. And if we finish it before you get a chance to vote, don't worry, because we'll have 4 more coming right after this one. Let's go ahead and finish and reveal.
All right, and the answer is maybe protons. So protons are positively charged. Neutrons are
neutral. And electrons,
no charge either way. Okay.
No charge. And electrons are negative. So the alliteration of P for proton, P for positive, that helps you remember protons are positive, and then neutrons are neutral, and then electrons, you just got to remember, like, it would be a negative thing if you got hit by a bolt of lightning, which is a current of electrons, and that will help you remember that electrons are negative. Let's go to the next one.
I like that. Okay, so our next question. If you mix elements, you can change one, say like lead, into another, like gold.
So is this true? If you take a couple elements together, can you actually create new elements if you mix them together?
By mixing them together here. Okay. Well,
if you could do this, Math Dad, because we don't know yet if it's true or false, we haven't revealed the answer, what element would you most want to make?
Gotta say, gold is worth a lot.
It's bizarre that gold is worth a lot because it's not very useful. It's too heavy and it's too soft for most of the things we want to do metal with. I just got to point that out.
Like platinum or uranium. There's some elements that are very valuable. So, although also kind of dangerous. So
I like titanium. I think if I were going to do a metal, titanium, it's difficult to work with because it's so strong and so hard, but it's a really cool metal. Yeah. So that I would pick that over gold. All right, let's reveal the answer.
Okay, and the answer listed here is?
Good job.
False.
Yes, this is false. You can, and when we talk about radioactivity in a couple weeks, we'll go into more detail here. It is possible to change one element to another, but not by conventional means. It does not happen easily, and you can't do it just by mixing things together.
So
if you took lead and you just mixed other elements into it, you're not going to be able to make gold. You have to have like a nuclear reactor and a collider to be able to.
Okay. So if you've got this one wrong though, there's some caveats in there.
It's true. Okay. Yeah. If you said true, you might have been thinking of like radioactivity and a hadron collider, different things like that. And then yes.
All right. Up next, true or false? Atoms are so small that they don't have any color. Ooh. Is that a true statement or false statement?
Oh, this one of them is winning by a mile.
Wow. Very popular answer. Okay, I think these guys were listening.
Yeah, we talked about this just pretty recently, so I bet you guys remember.
Yeah, it still boggles my mind, the answer to this question, but...
Oh, and can I just spoil it and keep talking because I'm excited about this? Did you guys know that viruses don't have color either? Sorry, if you're still voting and debating, I just spoiled it. Viruses don't have color either. They're so small. Even though they're made of, some of them, of hundreds of atoms, they don't have any color because they're
also so small?
They're also smaller than a wavelength of light.
But are they bigger than atoms?
Oh, yeah.
Because
way bigger than
they're
atoms.
Made up of atoms.
Yeah, because they're made of proteins, which have sometimes hundreds of atoms in them.
Gotcha. Okay, so the answer to this one was true. Atoms don't have any color. There's just no way for...
Because they're smaller than a wavelength of light, which is so small, so small.
All right. Up next.
Is this our last one, or do we have one more?
No, we got two more questions. All right. So the nucleus is made of which subatomic particles? Your options are protons, neutrons, and electrons.
And pick 2 of those. So it'll let you pick.
Did you just spoil it? Did you?
Oh.
You weren't supposed to say that, Science Mom.
I thought it... Never mind.
Yeah,
there's your hint.
It lets
Science
them
Mom.
pick 2. Oh, yeah. Okay, so 2 out of the 3. Science Mom.
Which 2
doesn't
are in
know
the
how
nucleus?
Questions work. All right, so let's see.
We've got protons, neutrons, and electrons. Which 2 are in the nucleus? And which one is not?
All right. Okay, we're just going to leave the poll on for another moment. And I realize that there's a delay on the video, and the poll actually might change on your device before we even get to it on the video.
Oh, yeah. And if that happens where we reveal the answer before you're able to vote, don't worry. Like we'll still see your vote after the fact. Like it'll still let you pick.
Yeah.
So if
or you might be able to vote before it would show up on the screen here. All right. Finish and reveal. And the answer is protons and neutrons.
Good job, you guys.
Those are the ones that make up the nucleus, and those are the two big ones, right?
They're the two bigger ones. Electrons, super small.
Big, but even though they're smaller than atoms, but compared to the electrons.
Compared to the electron is about 1,000 times smaller than the proton and the neutron. So the electron is way smaller.
Okay, that is crazy. All right, and then
last question.
Our last question. I kind of like this one. So, what is the name for the art of turning lead into gold? Your options are alchemy, chemistry, pyrotechny, and necromancy.
Pyrotechny. Pyromancy?
That's what I was going to do. Pyromancy. Apparently, I typed it wrong. It's hard to type these in. But,
Pyromancy is what Math Dad meant to say, which is like a big spoiler alert that that's not the right answer.
Who knows? It could be. But.
So the art of trying to turn lead into gold, which we learned a few questions ago, is actually not possible. Is that called alchemy, chemistry, pyromancy, or necromancy?
It would be pretty cool if it were possible, though. I understand why they wanted to do it so much. Like someone as respectable as Isaac Newton, you would think, oh, he would just do real science. But it turns out alchemy is the answer. And alchemy brought about the chemistry. It really just followed.
Yeah, it really did.
All right, so that's going to be the end of our polls. So kudos to you guys for doing a good job there. All right.
And now it is time for our demonstration. So I need to have you get that other screen up real quick, because for our demonstration, I actually have a video that I want to share. So there is this material that you might find in the grocery store called steel wool. Wait, don't play it quite yet.
Do it.
Steel wool is often used for cleaning out pots and pans, and it will come in these little sort of brushes. And you can see that it's made out of metal, just like this spoon is made out of metal. But look how small these particles are, or these pieces are. It's like the metal has been put into these thin wires. They're so small that if I hold up a thin wire,
it's like a hair.
You can't even see it. It looks like a hair. It's like the width of a hair. But if you put a bunch of them together in steel wool, this is really useful for scrubbing out pots and pans if you get like stuff that's burnt on a pan. So people use it for cleaning and scrubbing.
So I could find that at the grocery store.
You can find this at the grocery store. It's the same as this. And what I'm about to show you that we can do with it, our demonstration for today, is definitely a don't do this at home demonstration, because we're going to be using fire.
All right.
I'll show you my first attempt. It turns out that if you burn steel wool, it ends up being heavier than before you burned it. But the wind was going the wrong direction. I lit the wrong side, and so I burnt one, and then a spark went over because it was a little bit windy, and then I have sped up the view so you can see they're both just happily burning along, and the scale is not turning. Whoops.
All right, here you've got a battery.
If I set it on top of a battery.
What?
Whoa. It looks kind of like fireworks, and it just keeps spreading and spreading until it goes through all of the filaments. And this is what we're going to learn to understand in this chemistry course. By the end of this course, you will understand exactly how this happens, exactly how a battery is able to superheat a small filament of iron so that it burns, and exactly how that sets off a chain reaction so that the rest of the steel wool explodes into these little miniature fireworks of a chemical reaction.
So we don't need to bring matches when we go camping. We could just bring a battery and some
steel wool. Technically, you could. As far as fire starters go, this one isn't quite as powerful as others, but I do want to point out, look at the before and the after. Do you see how it changed color? So it starts out being light and sort of silvery, and then after you start this reaction, by the time it finishes, it will be a dark kind of rusty color, and that's exactly what's happening. The iron is rusting. You're taking iron that is not bound to oxygen, and you're turning it into iron oxide that is bound to oxygen. And this is why when you burn steel wool, it gets heavier. Then again, by the end of this course, you'll be able to understand really well exactly what's happening here.
Right.
And we'll go ahead and stop the screen.
All right, we're back.
And I want to check my phone real quick and see if anyone has any questions. And before we get into the Q&A, we just have a couple minutes left. I do want to share, we have a song. And for those who watched Quarantine, it is not the song that everyone knows the words to. I made Math Dad promise that that song would only be sung once on the last day of chemistry class, and he agreed. But he's been working on new songs, and for this new song, we have lyrics, but we don't have a tune yet. And we would like to invite you to submit your tune. So if you see this chemistry song, and if you have an idea for a tune that would go with it, take a video of yourself singing it, send it to us, or share it online and tag us. We would love to see it. So here's the tune. Subatomic particles. Here's a group of, or sorry, not the tune. Here's the words.
The words.
Here's a group of 3 protons in the nucleus, are positive, you see. Neutrons in the nucleus have no charge at all. Electrons in their orbitals are negative and small. So that's our chemistry song, and I will update the description to have those lyrics down there, and I'll post them online today. And we would love to hear your submissions if you have ideas for a good tune that goes along with that. Because Math Dad's come up with a tune, and I've come up with a tune, but we don't feel like it's the right tune. It's just not, we haven't come up with the right tune yet. So we need your help. All
right. So got a question here from Allison. So, well, go ahead. You go.
Okay. I'm going to take a couple questions that our moderators have sent us. We've got some great ones. Can you use any kind of battery with a still wool? That is a great question. You need to make a circuit. And when we talk about electricity, we'll go into a lot more detail about how this works. But this battery, you have the positive and the negative side by side. On a AAA battery or a AA battery, the positive is up here and the negative is down here. So on that type of battery, the only way that you can get this to work is by going like that and curving it around. And so any type of battery will work as long as you can make a circuit, but it happens a lot faster and a lot easier with this type of battery where the negative and positive are together, because then you just need to, and I'm not being a very good example doing this without gloves and safety glasses, you guys, apologies. And then you just need to touch them and you'll start to see that reaction happen.
I gotta warn you, it's a little stinky, so you probably don't want to do this indoors.
Don't do this indoors because it does not smell very good. A couple other questions we'll take real quick. What's the difference between mercury and quicksilver? Ooh, that's a great question. I would have to Google it real fast because I think that quicksilver actually might be a nickname for mercury, but I'm not 100% sure. So that would be something to Google. What's your favorite element?
Ooh.
Oh, that's such a hard question.
I gotta say, carbon's pretty awesome.
Carbon is pretty
what it can
awesome.
do, the different forms it comes in, and how many different roles it plays. Although I like oxygen. If you take away my oxygen, I'm an unhappy Math Dad. So.
I have to say, I really like, boy, there's so many good candidates. I really like iron because of how useful it is. And that's really what this is. Steel is just iron with a little bit of carbon mixed in. And you mix in that carbon and it makes it so much stronger and less likely to rust than if you just have pure iron. But iron is incredibly useful. So that's one. Are quarks smaller than atoms? I heard they are the smallest particles. Fantastic question, Logan. Quarks are even smaller than atoms. And if you look at a neutron and a proton for quite a while, they said, okay, we have neutrons, protons, and electrons, and those are the smallest you can get. But then we discovered neutrons and protons are made of quarks, particles that are even smaller. So there are subatomic particles even smaller than the smallest ones that we knew about 20 years ago.
Quarks and leptons.
Yeah, and maybe, I mean, if you go on to be a chemist and study particle physics, maybe you'll even discover a particle even smaller than the smallest one we know about now. That's kind of the exciting thing about chemistry.
There's your homework assignment, Logan. Discover a new particle by next time.
A couple more questions real fast before we end. If a positive charge hits a negative charge, do they cancel each other out? I love this question. So positive and negative do actually balance each other. And that's why if you look at a molecule, a single atom of hydrogen, it has a negative electron, it has a positive proton, and so the overall charge is nothing. It doesn't have a charge. And if you add an extra electron, then all of a sudden it has a -1 charge. So yeah, positive and a negative, they do cancel each other out. Good question. And I see that Kevin says, I have some steel wool. Make sure that you get approval from a grown-up before trying anything like this. That's like the most important thing that I want you all to know from today. Permission before you do anything with fire. That's absolutely required. Another question, is the mercury that was used in thermometers pure mercury? It all depends on what type of thermometer it is.
Mm.
Nowadays, if you go to the pharmacy and you get a thermometer, there's going to be a silvery substance in there that looks like mercury, but usually it's not. Usually there's a different compound that's safe, so that if the thermometer broke open, you wouldn't need to worry about someone inhaling particles of mercury and getting mercury poisoning. But 40 years ago, yes, they did use pure mercury in thermometers. And if they broke, usually people were okay, but you don't want to risk someone getting poisoned with mercury. So that's why we don't use mercury today. And another good observation, the denser an object is, the harder it is to catch on fire, because fire needs air. This is an excellent question. Shout out to whoever asked that question. Science Mom Jody forwarded it on to me, that comment. And this is true. This is the big difference between our spoon and our steel wool. Okay. So, Math Dad, this is a stainless steel spool. Is it made out of iron with a little bit of carbon? Yes.
Yes.
This is steel wool. Is it made out of iron with a little bit of carbon?
Yes.
Yes. This one, we cannot light on fire. This one lights really easily, and it's all because of how much oxygen is around. And if we took this spoon and we pulverized it into a very fine powder, and then we threw that powder up into the air and lit a spark, it turns out that it would burn too. And that's kind of the concept behind fireworks, to tell you the truth. You get small little particles up in the air, surrounded by lots of oxygen, and then you ignite them and you see the display of fireworks. So particle size makes a big difference. We'll take one more question and then we are out of time. So I see Megan asks, what is mercury made out of? It's an element. And the cool thing about elements, which we'll be talking about more on Thursday, elements are made out of just the atom of that element. So if you have pure mercury, it's only made out of mercury atoms.
So something like water is made out of
oxygen,
H2O, so it's hydrogen and oxygen, but mercury is just mercury.
Just mercury, yeah, which is pretty cool. We will be talking more about this on Thursday. We're going to dive into what the different elements are and how you can tell the difference between one element and another and why they react so differently. We're going to be learning all about the periodic table. I'm excited for our next lesson. I hope you guys enjoyed this one, and we are looking forward to a fantastic journey through chemistry. As I mentioned before, by the time this class is done, you will understand everything behind this cool science demonstration. Why a flow of electrons superheats metal, why that metal is ready to spark, and what other types of metal would react and what types wouldn't, and how it all relates to the protons, neutrons, and electrons that you have inside something like this. We'll see you on Thursday.
I can't wait. Bye, guys.